Good afternoon, everyone. My name is Austin Roy. I'm the leader for Group 4 for the vapor compression refrigeration cycle. This experiment we're not doing until like March 2nd, so it's going to be a little while. I included a lot of graphics to make sure we can kind of like have a little picture memory to remember what's going on. So, what we're talking about is the purpose of the experiment, why we're doing it, go over some concepts. You see a lot of stuff from thermo in this experiment. The actual procedure, what we're going to be doing, also talk about the apparatus we're going to be looking at, and then we'll look at some of the sample calculations and some conclusions. So the actual purpose of the experiment, we're going to learn, we're going to relearn some topics from thermo, mainly second law, refrigeration cycle, and then we'll also learn about the TRCVC unit. Basically, it's just a closed loop refrigeration unit. And then the actual coefficient of performance, we'll look at the efficiency of that unit. We'll be able to describe it using a pH diagram. And then we'll also look over the efficiencies and any uncertainties we see within individual components of that actual unit. It'll have temperature sensors, pressure sensors throughout, so we'll have data to work with. So, background, refrigeration cycle, why is it important? Why do we care about it? Well, it's great because it allows us to move heat from a low temperature reservoir to a high temperature reservoir. It's why we're nice and cool in this room and not burning up like we would be outside in Louisiana. So here we have a little quick idealized PD chart. Main thing I want to show here is during evaporation, we have our constant adiabatic pressure. As our volume increases, we're absorbing heat into the system, and then after we introduce work during compression, we're actually going to, during condensation, we're going to reject heat while compressing our working fluid. And then we have a pH chart. Main thing I want to show here is that we're going to be introducing enthalpy from 1 to 2 with the compressor. That's because we're introducing work into the system. And then y'all saw this TS diagram for Chris. Apparently used the same Google search. Main thing I actually want to show you all from this, the throttle, the expansion valve, 2 to 3. We're actually introducing some entropy, and that is because the viscous heat generation is caused by friction and the working fluid coming through that expansion valve. So, apparatus for the experiment. First thing I want to talk about is the compressor itself. It's referred to as a hermetic compressor, and the fancy term for just saying it's sealed, airtight. What's cool about it, the motor and compressor are actually connected by the same shaft, so that allows it to be highly portable, and supposedly it requires less maintenance than like a belt-driven separate motor and compressor. It is computer controlled, so we'll have data going in and out, and we'll also have control over how it operates. We have a little schematic kind of showing you the inside. I thought that was pretty neat. It won't be exact to the one we have in the lab. Supposedly, this is what we're going to be looking at in the lab. It could differ a little bit, but it'll be that little container in the center. Purpose of this, we're increasing the pressure of our working fluid. We want to increase the corresponding boiling point, and yeah, it's pretty much it. It's a compressor. So condenser and evaporator. The point of the condenser is we're going to have a high pressure and temperature gas. We're going to be rejecting heat from that, and then we'll be phase changing into a liquid. Evaporator, low pressure and temperature going in, absorbs heat from our low temperature reservoir, and then it'll start boiling. So in retrospect, I probably should have split this up. It's a little cluttered slide, but we'll just kind of break it down. This is a really cool part. This is the thermostatic expansion valve. So just kind of breaking it down, I said this is where the magic happens. So what it is, it's by and large, it's just a restrictive orifice. Coming from the condenser, we have that high pressure, high temperature coming through, and then we're going to essentially almost like flash it into the evaporator. So that saturated liquid is going to become vapor, and what's going to happen is we're increasing the volume rapidly, and we're lowering the temperature and pressure of our working fluid. And so once we do that, it's going to go through the evaporator, and you're going to be able to cool off whatever temperature medium you're working with. So what's special about this TXV valve is it actually has an automatic control for your flow. And kind of what we're looking at here, what we're interested in, is this little sensing bulb going all the way back to your your actual expansion valve, and what's cool about this is they actually have a little amount of refrigerant in that sensing bulb, and it's in thermal contact with the outlet of the evaporator. And what happens is, depending on your temperature, what you're looking for, your parameters, it'll either cool up or heat up, which will increase or decrease the pressure, and it'll go through a capillary tube that once again connects to your expansion valve, connected to a diaphragm that, increase in pressure, it'll push on it, decrease, it'll pull back, and that actually pushes on a pin within the expansion valve, which will control the flow. And all this is happening automatically, while your experiment's taking place. It's a pretty neat device. If it were to fail, you could have issues with liquids going to your compressor. Compressors don't like that. Compressors are for your gases, pumps are for liquids. So just kind of quick, going over the experiment procedure. This experiment is going to be nice and quick for us. Groups 2 and 4 are going to be out of here pretty quick. The actual screen we're going to be looking at on the computer looks like this. I won't be able to decipher it for y'all because I haven't seen it myself. But we're going to start the software. We're going to make sure the evaporator condenser are on. We're going to set our water flow rate, which is our medium of exchange, to 5 liters per minute. Turn on the compressor and set it to 40%. I haven't seen it, whatever that ends up being. And then we'll allow it to stabilize and record our data from that. And then we also have the second part to this, exercise 2. We're going to repeat the same steps we did before, except we're going to actually change the flow rate to the evaporator from 3 different values, 3, 4.5, and 6 liters per minute. Each one of those we're going to allow the system to stabilize, and then we're going to record our data for each. And that's kind of like, this is what it may look like. I haven't been there, I'm not quite sure. This is what they showed us, but it'll generally look like this kind of setup. What we're mainly interested in here is the coefficient of performance. We're going to be looking at the enthalpy before the evaporator, after the evaporator, and then that's also before the compressor. We're looking at the enthalpy after the compressor. Coefficient of performance is the ratio or magnitude of our cooling over the work we input into the system. In conclusion, just coefficient of performance is just the efficiency of our heat pump. That's what we're mainly interested in for this experiment. And also heat can be transferred from a low temperature reservoir to a higher temperature reservoir if we just insert some work into the system. Any questions? Go ahead.
Which part of this experiment interests you the most?
Well, I probably made it kind of clear. The expansion valve was probably the coolest part. I thought it was pretty neat that they had like an automatic system where you don't have to do anything. It'll take care of itself. I'm really curious to see what that's going to look like in the lab. But yeah, won't do that. Learning how they do that with the diaphragm, pretty interesting stuff.
Good deal.